Hi. Hi. All right, so last time we started in on chapter 4, we worried about whether or not a matrix is non-singular because it seems to be such a key property. And so we were looking for basically a formula to determine non-singularity. Now, the way we phrased it last time is that we're actually finding a function to determine non-singularity, and we're eventually going to determine we're eventually, going to develop a formula that determines non-singularity, a formula that calculates the function. But at the moment, we're worried about formulas that determine non-singularity because as you see in the check-in, we already have the 2x2 version and the 3x3 version of those formulas, and we're determined to use them. So I simply want to emphasize that we're describing the non-singularity of matrices, non-singularity versus singularity of matrices, and so that's what the check-in is about. All right, so a relatively easy one here just asks me to calculate the formula. So I have a matrix. It is 2, 1, minus 4, 2. 2, 1, minus 4, 2. Okay, and so I'm going to calculate AD minus BC. So that's 2 times 2. 2 times 2. Whoops. 2, 1. Oh, minus 4 minus 2. I'm sorry. 2 times minus 2 minus 1 times minus 4. So I get to minus 4 plus 4 equals 0. And in fact, when I think about it, the second row is minus 2 times the first row. So we have this is singular. Okay, so we have a formula that determines singularity, and in the 2x2 case, it's worth memorizing AD minus BC. The 3x3 case, on the other hand, it is not worth memorizing, or at least not worth memorizing unless you're going to do an awful lot of these. So let's see, I wrote it down here. A, B, C, D, E, F, G, H, I equals, and I don't have it memorized, so A, E, I plus B, F, G plus CDH, and then subtract HFA, subtract CDB, and subtract GEC. And again, we went over last time. I gave a little bit of a warning. There are various mnemonics that you can use here to try to describe what the what these formulae is. You do something with the diagonals and the backwards diagonals, but I'm going to skip over that because it sometimes causes confusion, and I'm just simply going to describe it as just a kind of involved, not grossly involved, but a kind of involved formula. All right, so now when I go to look at 1, 3, 1, 2, 0, minus 1, and 0, 1, 3, and as opposed to the first problem, it was pretty clear that the second row was a multiple of the first. Here, I don't know, it could be that 5 times the first minus 2 times, I don't know, some kind of thing. So I'm going to do the calculation and see if I can do it. It gave me a little trouble when I was trying to do it here in preparation. So 1 times 0 times 3 plus 3 times minus 1 times 0 plus 1 times 3 times 1. And then the minuses are 1 times minus 1 times 1 and 3 times 2 times 3 and 0 times 0 times 1. So what do we get here? That's a 0, that's a 0, that's a 3. That's a 1. And that's a, forgive me, that's a 2. I'm sorry, 2. And that's a 2. There we go. And that's a 1. And that's, let's see, 3 times 3 is 9 times 2 is 18. And that's a 0. Okay, so when all the smoke clears and when I correct the mistake that I made up here, I've got 2 and 1 makes 3, minus 18, so we're looking at minus 15. And I don't actually really care at the moment in this section. I don't care about the size. We'll care about that in the next section. But at the moment, all I care about is whether it is 0 or not. And it's non-zero, so non-singular. non, and non. So modulo, copying down the wrong digit, the calculation is reasonably straightforward, although the formula is a little bit hard to remember. Nonetheless, the goal is to come up with a way of determining non-singularity. At least in principle, determining non-singularity. Okay, so let's see here. We're ready for the material for the day here. Whoops. Again, I hit the wrong button. I hit the wrong button a lot. It's a little discouraging. There we go. So I'll remind you where we are. We are trying to figure out here. We already have uniqueness, so we are trying to figure out a formula that calculates the determinant. And the reason why we want a formula that calculates the determinant, we already have Gauss's method, and it works very well, very fast, so it's a good method. The reason we want a formula to calculate the determinant is because we want to prove that there is a determinant function. So remember, we're in this somewhat odd circumstance where we defined, it wasn't clear what the formula was. So instead we defined the determinant function by some properties. Those properties allowed us to do Gauss's method. But when you define a function by properties, it isn't perfectly clear that there is such a function, nor is it perfectly clear that there's only one such function. You have to verify those things. So we've already verified that if there is a function, there's only one. So we verified uniqueness. And now we're going to verify existence. In order to verify existence, it's a little more involved. We're going to build up a sort of technology to use the properties of the determinant as described in the definition to calculate the value. So basically, we're going to build a formula, except that it's more involved than just saying, here's the formula and check. Okay, so the real lesson here, the lesson for today, is that this is a course called, remember, it's called linear algebra, and the determinant function is not a linear function. So it is not the case. Do you see the word not there? Not the case that the determinant of k times t is k times the determinant of t. It just isn't. Here's an example here. So I took 3 minus 3, 9. I doubled it to get 6 minus 6, 18. And I calculated the determinant of this fellow. You can imagine I used the formula that I just used in the check-in. And it just simply doesn't double. It just simply doesn't. It doesn't. That's all there is to it. Okay? So here, if you look at, I doubled the 3's minus 3, 9 to get 6 minus 6, 18. I doubled the 1, the minus 1, 7 to get 2 minus 2, 14. I doubled the 2, 4, 0 to get 4, 8, 0. I don't get double the determinant. I just don't. Instead, what condition 3 says is that the determinant scales one row at a time. So, if you take the 6 minus 6, 18, and you bring it back to the 3 minus 3, 9, that brings out a 2, and the 2 multiplies the entire determinant. So bringing a 2 out of one row multiplies the entire determinant. If you go on and bring the 2 out of the second row, to make a total of 4 at the beginning here, a product of 4, then what you get is, again, doubling, bringing 2 out of one row, out of a single row, doubles the entire determinant, and finally bringing 2 out of the bottom row, making the 480 into 240. Bringing 2 out of the bottom row, again, doubles the entire determinant. So in fact, what's the relationship between these two numbers? Well, this one is 8 times that. So the lesson is the determinant function is not linear. Instead, it's one row at a time. These k's come out one row at a time. Determinants are not linear. With scalar multiplication, the scalars come out one row at a time. Well, a person can say, well, okay, well, I remember linear. Linear involved bringing out scalars and also involved breaking along a plus sign. So what happens with pluses? Good question. Of course, pluses and times are related in the usual grade school way, that if you have an apple and an apple, that's 2 times the apple. So here, if you, for example, imagined the 2 times written this way, or imagined it written this way, then that corresponds. See how the determinant is breaking along that plus sign in that row? The determinant is I wrote 2 rho I as rho I plus rho I, and then I got 2 times the determinant over here by writing determinant with a rho I and determinant with a rho I. So this suggests that the determinant is breaking 1 row at a time for pluses as well as for scalar multiplies. Now this doesn't prove, but it strongly suggests. And in fact, it's true. So determine a function that satisfies the 4 conditions that we saw in the last video is not linear, but it's what's called multilinear. Here we see that the k on a single row comes out to be k times the entire thing. And here we see what we were just exploring on the previous slide. A plus on a single row comes out to be a plus of the entire things. A k on a single row is k times the entire thing. A plus on a single row is the plus of the things. So determinants are linear sort of 1 row at a time. And that's called multilinear for the obvious reason. You can't call it linear because it just simply isn't linear. And I got to verify here the 2 conditions that are listed there. Property 2 is just simply condition 3. So there's no need to verify it. I have to go on and verify property 1. There are 2 cases. Again, we saw this last time. This material is a little bit more abstract than some of the material, especially we saw in the beginning of the class. But part of the goal of the class is to raise a person's ability to cope with abstractness. So we're periodically salting in a little bit of more abstract material, helping a person to get comfortable with seeing these kind of higher level thinking sort of things. All right, so there's going to be 2 cases to show that condition 1 is true. There's going to be 2 cases. You look at all the other rows, not the v plus w row, not the v row, not the w row, all the other rows, the ones that are called with the Greek letter rho. So row 1, row 2, all the way up to row I minus 1, row I plus 1 through row n. That's a set of rows. It's a set of row vectors. If that set is linearly dependent, if, for example, row 1 is 3 times row I minus 1, if that set of rows is linearly dependent, then that matrix is singular because it doesn't involve v plus k, it involves the other rows. That matrix is singular because it doesn't involve v, it involves the other rows. And that matrix is singular because there's some linear dependence among the other rows. All 3 would be singular because I have a linear dependence among the rows, a linear dependence among the rows, and a linear dependence among the rows. So I'm looking at 0 equals 0 plus 0, so the statement is true. Okay, so if the set of other rows is linearly dependent, then the 3 matrices are singular. The determinants of everybody is 0. 0 equals 0 plus 0, we're done. So clearly the other case is that the set of other rows is linearly independent. So we've been in this game for a while now, and I think a person can see what to do, or at least have some idea of what to do. I know it's abstract, but still a person can have some idea of what to do. When you have a set of n minus 1 many linearly dependent things, what you think to do is to throw in one more. So you have a set of n minus 1 linearly independent things. I think I might have misstated it. Set of n minus 1 linearly independent things. And you think to throw in one more and get a basis. So that's the plan. We think to throw in one more, I'm calling it beta, to get a basis. Of course, I'm going to express v and w with respect to that basis. Again, we've been playing this game for a while now, so it has a certain, the tunes have a certain familiar rhythm. So we express v and w with respect to that basis. I chose vi for the coefficient of beta and wi for the coefficient of beta here. And I'm comparing. There's the v, there's the w, there's the v plus w. You consider the left side, and you expand the v plus w. There we go. Oh, I meant to click back and show you the left side. Remember the left side has a v plus w in it? So you've got the determinant. There's the v plus w part. And I have a row I, and there's a row I. So I'm going to do Gauss's method on this. I'm going to take minus v1 plus w, row 1, added to this row right here. Again, minus V1 plus W1, row 1, added to this row right here. And of course, what that'll do is that'll get rid of this. Same thing, I'm going to take minus Vn plus Wn and add it to this row right here. Minus Vn plus W, oh, so I said that wrong. Minus Vn plus Wn times this row, add it to this row right here. Again, because I said it wrong. Minus Vn plus Wn, add it to this row. Minus Vn plus Wn times this row, add it to this row. As I go through the Gauss's method steps, and I can eliminate everybody except for beta. I go through the Gauss's method steps, and from this determinant, I eliminate everybody except for the beta part. Okay, all right. Well, there's a multiplier, so bring it out. I brought it out. Vi plus Wi, I brought it out. Now break this regular grade school, maybe it's junior high school, distribution along this plus. There's Vi times the determinant plus Wi times the determinant. And now bring the Vi back in, bring the Wi back in, put all the row 1, row 2, row 3 parts back together using the combination operations, which it doesn't affect the determinant at all, and you're back to the original 2. Okay, so that was a little bit tricky, but not brutally tricky, but a little bit tricky. Okay, so before I go on, though, I want to make a remark. I know that in this internet age, a lot of times when people are studying material, they'll Google around and they'll find something here, find something there, and piece it together. I often do that when I'm trying to learn new material. So here's the definition of multilinear, and here's the original definition that we gave of the determinant function. I have to click back a little bit. I'm sorry. There. Many authors, if you go and look on Wikipedia, or you go some other linear algebra material, many authors will use multilinearity in the definition of determinant. It's just a different approach. I like this approach right here. I like this particular definition where you derive multilinearity from it. It's a little more involved sometimes, but I like it because it seems less abstract. To a person who is not all that comfortable with abstraction, because for many folks, this is the first course where you see abstraction. For such a person, this at least seems related to Gauss's method. And then from that relatively familiar definition, then we get the property of multilinearity. So we proceed sort of from familiar to new material as opposed to sort of jumping right in feet first to new material. Just a different approach gets you the same answer. So what you're seeing when you click around to other sites, they're all getting the same answer. We're just sort of somewhat different ideas about how to do that. Okay, so what's the point of multilinear? So here's the point of multilinearity. So it got a little abstract for a moment. We're back on solid computational ground. Here we go. I'm going to take 1, 2, 3, 4 and expand it using multilinearity. So 1, 2, 3, 4. 1, 2 is the sum of 1, 0 and 0, 2. So I'm allowed to break 1, 2, that row, break into two separate determinants, the determinant with 1, 0 and the determinant with 0, 2. I mean, I could have broken into 1, 1 and 0, 1. I could have. That will turn out not to be fruitful, but I could have done that. But instead, I broke it into 1, 0 and 0, 2. Well, you see the game. 1, 0, I can look now at the 3, 4 row and break that into a 3, 0 and a 0, 4. So the 1, 0, 3, 4 breaks into these two. The 0, 2, 3, 4 breaks into these two. And what I've got now is 4 matrices. You could say, well, you made 4 problems out of 1. That's true. But some of these problems are very easy because look, this one, the 2 rows are multiples of each other. So that's 0 right away. There's a linear dependence among the 2 rows. That right there must be a singular matrix. Boom, 0 for a determinant. Right here, those 2 rows are multiples of each other. So that's got a determinant of 0. Boom, done. So I'm down to 2 different relatively easy matrices. This one here, what's the determinant of this matrix? Well, it's an echelon form matrix, so you multiply down the diagonal. So 4. What's the determinant of this matrix? Well, it's not echelon form, but one row swap will make it echelon form. So you do one row swap, remember the minus sign in your mind, And now it's a diagonal matrix with 2's and 3's on the diagonal, so the determinant is 6. So in total, we have a determinant of minus 6, because a swap followed by multiplying the diagonal gives you minus 6. So we get 0, 4, minus 6, 0. Add the 4 and the minus 6 together, and you've got a minus 2. So I turned this is not a complicated problem, but a relatively complicated problem into 4 relatively easy problems. Okay? Next one, 3 by 3. So you've seen the game here, so you can play the same game. I broke this up into here. You break the 1, 2, 3 up into 1, 0, 0, 0, 2, 0, and 0, 0, 3. Then for each of those 3, you break it up into 4, 0, 0, 0, 5, 0, and 0, 0, 6. And for each of those, what's that, 9 so far? For each of those 9, you break up into 7, 0, 0, 0, 8, 0, 0, 0, 9. And you get a whole bunch, 27 of them in total. You get a whole bunch of determinants, a lot of them, exponentially many, 27 determinants. But each of them is straightforward. So just to go through a couple here. So here, first row, second row, they're multiples of each other. Boom, 0. First row, second row, they're multiples of each other. 0. First row, second row, they're multiples of each other. 0. First row, third row, multiples of each other. 0. Second row, third row, multiples of each other. 0. So what you're seeing is I'm getting a whole lot of problems, but most of them, not all of them, this one isn't 0, but most of them are very easy. The 1, 5, 9, what's the determinant of that? Well, 5 times 9 is 45. Here, first row, third row, multiples of each other. Here, here, one row swap will make this matrix be a diagonal. So the determinant of this is negative sign 1 times 8 times 6, so that's negative 48. Okay, so the determinant of this, boom, 0, because second row, third row. Well, so like that. You proceed along in this way, sometimes doing row swaps to get yourself an echelon form matrix, but a lot of times just saying, boom, 0. And you get a relatively simple answer. So anytime you have 2 or more rows that are multiples of each other, the determinant of the matrix is 0. So I've reduced to a sum of determinant where each matrix is all zeros except for a single entry in each row and each column. Can we go back here? Over here, there's an entry here, actually 3 entries in the first column, so that's a 0. There's 2 entries in the first column, so that's a determinant of 0. 2 entries in the first row, in the first column, so that's determinant of 0. Here, 2 entries in the second column, so that determinant is 0. Down here, 2 entries in the third column, so that determinant is 0. So what we're getting then is we end up with everybody 0, except for if you have a single entry in each row, a single non-zero entry in each row and column. So there's 3 places to put the first. There's 3 columns in which you could put the entry from the first row, and then there's 2 columns remaining, and then there's 1. So there's a total of 6 of those. So the 27 that I got, almost all of them are 0, except for 6 are non-zero, or potentially non-zero. And there we go. And those 6 are relatively straightforward. Mentioned that that one is 45. Mentioned that that one is minus 48. I apologize. Minus 48. That one is minus 72. That one is, doesn't that one take 2 row swaps? So that one's plus 84. That one is, I don't have to go back and change these minus signs and plus signs. I apologize. I flubbed this up. That one, so if you take 1 row swap or 0, if you take 0 row swaps, then you're good. You just multiply down diagonal. If you take 1 row swap, then you have to have a minus sign. If you take 2 row swaps to go back to a diagonal matrix, then you're back to plus. 3 row swaps would take you back to minus. I apologize about these pluses and minuses. That's a typo. I'll have to fix that. So after bringing out each entry from the original matrix, we're left with matrices that are all zeros except for a single one in each row and column. So this determinant right here inside 48 is what it'll be. But the determinant of this matrix will be -1 because it takes one row swap to bring this to the identity. Determinant of this one, I'm sorry, I really should have said this. The determinant of this one is -1 because it takes one row swap to bring it to the identity, swap row 2 and 3. Determinant of this one is +1 because it takes two row swaps to bring it to the identity matrix. Determinant of this is -1 because it takes one row swap to bring it to the identity. And the determinant of this is +1 because it takes two row swaps to bring it to the identity. So we have a sum this is all correct, but I should have put in the plus and minus ones here. So I got to go in and make a correction and mark that it's pluses and minus ones. Okay. Okay, so very good. So what we've got then is we develop multilinearity, and multilinearity allows us to break a determinant up into many smaller jobs, each of which is either 0 or very straightforward. Okay, very good. So we'll stop there and then and work with multilinearity on the homework, and then we'll go on and work some more with multilinearity to come out with the formula for for a determinant. We won't use that formula to calculate determinants because it's too big and awkward. We'll always use Gauss's method, but of course there's an advantage to having a formula. The advantage is that it shows that there is such a function because the formula computes the function. Okay, very good.